Okay, so this is going to be our very second, no, third topic so far. This is going to be our third topic, and this topic is based on one young gentleman. Is he young or old? Anyway, he's dead. So Newton,
Yeah.
Isaac Newton. We're going to study some of his laws. And I don't know. I've never read his book before. It's a mathematical principle of so. So I've forgotten the title, but it's in the book I gave you. Maybe one day
Um.
I'll just download this actual book to see what he was actually doing. The guy is super intelligent. Huh. So he brought about three laws, basically three laws of motion. These laws governs motion. Some of them they've not been proven yet to be true, but it's an assumption that is true. So we're going to go through the three laws. Like I told you the other time, the focus is going to be on the second law. When we move to momentum, the focus will be on the third law. And the first law, we've done something on the first law already, so that shouldn't be a problem. Okay, so there is a very first law. So the first law states that everybody remains in a state of rest or in uniform motion in a straight line unless acted upon by an unbalanced force. So if an object is on the table, like the way your PC is on the table,
Mm.
if you don't stack the PC will never move. Are you getting me?
Yes.
So if you don't give this PC a push or a pull, this PC will never move. So every object would like to be in its state of rest, sorry, unless maybe acted upon by an external force. Also, it goes on to tell you that okay, if the object is not at rest and it's in uniform motion, it's going to stay in that uniform motion unless acted upon by an unbalanced force. This part is where the issue with the proofs comes in because we can't really prove that on Earth.
No.
Because at every point in time, there's going to be a resistance. There's going to be a
Mm.
force acting on the particle. The only place that it's assumed that this can be proven will be outer space, where maybe an object starts to move with, let's say, a velocity of 3 meters per second. After 1,000 light years, it's still going to move with that same velocity. So that is what the law is saying. Unless maybe an asteroid comes in contact with, I don't know, just something that will will come in contact with the particle. This particle is never going
Mm.
to change its speed. So that is the first law. Now, when we talk about uniform motion, what is uniform motion?
Um. That means the object is moving at um the same speed like it
The
started
same.
with.
So initial speed is equal to final speed. Do you agree?
Yes.
The initial speed of the particle is always going to be equal to the final speed. From the Stewart equation, V equals U plus AT, my favorite, V equals U plus AT. V is equal to U, so V minus U um, A over T. I'm finding acceleration over there. If
Mm.
V is equal to U, a number minus itself is actually zero, right?
Mm. Yeah.
So the acceleration is zero. So the first law, one of the main things we're going to pick up from the first law is that when object is when object is having it's in uniform motion. Let me put it this way: when an object is in uniform motion, the acceleration of the particle is zero. Are you getting it? This one is
Mm.
not always clear. That is what creates problems when it comes to the the first law of motion, because the object is moving. If the object is moving, people just have this notion that okay, if there is speed, there is acceleration, but that is not always true. That is not true. There can be speed without acceleration. When there is no change in speed, there is no acceleration. So once the question talks about motion, the student automatically thinks that there is going to be some level of acceleration over there. So you should take note of this when the object is in uniform motion. the acceleration of the particle is zero. Similarly, when the object is not in motion, this one is very clear to see. When it's not
Mm.
moving, then there is no acceleration. So at rest, the acceleration of the particle is zero, and in uniform motion, the acceleration of the particle is also zero. Is that okay?
Yeah.
So that is the main two things we need to get out from the first law. Okay. Now let's see what we can do with the second law. Um, we've got a lot of things to do today. Okay, so the second law of motion. This can be transformed in a lot of ways. The simplest would be that the net force of an object is equal to the product of the mass and its acceleration, the net force. But let me read what I've got over here. Newton's second law states that the resultant of the forces acting on a body is equal to the mass of the body multiplied by its acceleration in the direction of that force. So it's going to be in the direction of the force involved. So, like I said, this comes in a lot of ways. The second law can be described using momentum. The rate of change of momentum is directly proportional. Those kind of things. But because we don't know anything about momentum, I'm not going to put anything with momentum over here. Now, the same law can generate to impulse. This is going to lead to impulse is equal to change in momentum. But because we're not really doing anything on impulse, anything on momentum, we just stick into the basic definition that says that a force of an object, the net force on an object is equal to the product. So this is not just a force, it's a net force, the leftover force. After doing your resolution, the net force of the object is equal to the mass of the object times its acceleration. So that becomes the second law of motion. We're going to solve questions using this. Actually, majority of the questions you'll be solving will be using this idea. So I'm not really going to say much about it now. When we start solving the questions, we start talking about this. Is that okay?
Yeah.
Okay, good. Let's see the third law. The third law. This is called the law of karma. Do you know karma?
Yeah.
Okay. So, well, this is how I see it. I see it to be karma. Whatever you do goes back and comes back to you. Those kind of things. So you do good, uh, it goes back, and eventually someone do the same thing to you, something similar. Okay. So the third law says that for every action there is an equal and opposite reaction. For every action there is an equal and opposite reaction. This idea is going to be used to prove the conservation of momentum, which says that the initial momentum is equal to the final momentum of an object. So we come back to this third law when I'm teaching you momentum. So basically, this third law states that for every action, there is an equal and opposite reaction. So that is the law of karma for me. Okay. Now let's start with the interesting stuff, like solving the questions. This question is actually very simple. A sled stands on a smooth horizontal icy ground. The sledge has a mass of 35 kilograms. If the force of 105 newtons acts on the sledge, find its acceleration. So in most cases, drawing a force diagram will be very good at this stage. So majority of the questions I'm going to solve with you, I'm going to try my best to at least bring out a diagram over there. Now, the word smooth, what does it imply?
No
Yes,
frictional force.
no frictional force. Good, no frictional force. So let's say that this is my surface. It's very smooth, yeah. And there's my how can sledge be? Okay, okay. So there's my, let's say, sledge or something, and this has got a mass of 35 kilograms. Let me hide this one. This has got a mass of 35 kilograms. So we were told that if a force of 105 newtons acts on the sledge, a force of 105, let's say there's a force 105 newtons, acts on this particle, find the acceleration. Note that the acceleration of the particle, sorry, the using the The second law says that the net force, not just the force, the net force on the object is equal to the product of the mass and its acceleration. Now, in this case, what's the net force over there?
105.
105, because there is no resistance to this force. So assuming there was a resistance, you should know that it's going to have an effect on our calculation. Is that okay, Derek?
Yes, yes, please.
105 is our net force, and the mass of the object is 35 times the acceleration. You divide both sides by 35, and you should get something nice for the acceleration. What is A?
3 meters per second square.
3 meters. Okay, so there is 3.
Mm,
Okay, so that answers that question. Any question so far?
no.
Okay. And you should know that you are not never going to get a question like that in your
Mm,
final. That is just a concept building. You understand, right?
yeah.
Yeah. I can't just start with the crazy questions over there. I'll get you confused. So let's see what we can do about this one. A man pushes a box on horizontal ground with a force of 220 newtons. There is a frictional force of 60 newtons opposing the motion. If the acceleration of the box is 12 meters per second squared while it's being projected, calculate the mass of the box in kilograms. Calculate the mass of the box in kilograms. So let's see. First, we've got an object with a mass which we don't know. So let's say the mass is m. There is a vertical force acting in this direction, and the force is 240 newtons. And there is an opposing force which we're given as 60 newtons. Now, we're told also that the acceleration in this direction is 12 meters per second squared. We should now find the mass of the object. Again, from
So,
the yeah,
does that mean that projection is not always upwards?
no, 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 no.
Mm,
It's not
mm,
always the case. Yeah.
mm,
So projected and another way to see this is the object was placed in motion. Are you getting
okay.
it? You're getting something
Yeah.
that an object was placed in motion, so it can be placed in motion on horizontal ground or on a vertical ground.
Mm,
Okay, so the net force again, the net force is going to be equal to the mass times acceleration. In this case, the net force is going to be 240 minus 60, 240 minus 60 times m times 12. So let me take this opportunity to talk about something that will really come into play when we're dealing with connected particles. With connected particles, we always look at the direction of motion. In this case, the motion is going in the direction of 240 newtons. Unfortunately, we weren't given the question bar. Um, Looking at the force diagram over there, that should tell you that that's going to be the direction of motion. So whenever
mm,
you get a question like this, it should be the direction of motion minus all forces towards the direction of motion minus the forces outside, let me say the forces opposing the direction of motion. So you can write this one down. It will come into play when we are dealing with the connected particles. So the direction of motion, first identify the direction of motion and all the forces in that direction minus the forces in the opposite direction. That will give you the net force. I think you know what I'm talking about
yeah.
with that forces already, so you should know what I'm talking about. So that's the direction of motion minus all other forces. Not all other forces that opposes the direction of motion. So that is just by the way. Now let's do the calculation and let's get our mass. So 240 minus 60 divided by 12, and that should be 15 kilograms. The mass is 15 kilograms. Is that okay?
Yeah.
Okay, so that is the second question. Let's see. I really fast. We've got about 13, 16 questions to solve. Um, in a game of curling, the heavy granite stone of mass 20 kilograms is projected across an ice rink, ignoring friction. If the acceleration of the stone is 2.4 meters per second, calculate the magnitude of the force projecting it. This is interesting. Okay, so again, let's try to draw a force diagram. This time, let me use a circle. A stone can be a square or a rectangle. So this is 20 kilograms. 20 kilograms. Let me express myself. Okay, 20 kilograms, and we're told that there is no friction, and there's the direction of motion. Let's say that's the direction of motion with an
Mm.
acceleration of 2.4 meters per second squared. But Derek, without me telling you that this acceleration, let's say I didn't even write the unit, will you be able to tell that that is acceleration?
If you
Yes.
do
Assuming
like
I just
the arrow
yes,
with the
yes,
arrow there, yeah.
yes, yes. Okay, the double-headed arrow is acceleration. The
Mm.
single is velocity. Okay, so yeah, this is what we've gotten now. Any ideas as to how we're going to do this? If the acceleration, I
Um,
think the next force over there is going to be the next part wasn't given, was it?
yes, that's what we are supposed to look for.
Right. Okay, okay. So let's say that there is a force F. So I can say that F equals to ma, and the mass of the particle is 20, and its acceleration is 2.4. This is pretty easy. So 20 times
48.
4, so 48 newtons. So that
Mm.
answers that question too. That answers the question. Okay. So question number 4. A wooden block of mass 5 kg is at rest on a smooth horizontal table 1.6 meters from the edge of the table. The block is pulled directly towards the edge by a horizontal spring. The tension in the string is 1 Newton. Calculate the time taken to reach the edge of the table. Now I'd like you to try this one. I'll
Mm.
solve the difficult questions with you, so solve the easy one. So let's see if we can solve this one. There's actually a combination of two things. Did you notice? They are merging two concepts.
Mm.
Yeah, laws of motion and which one? Are you seeing
Um,
kinematics over there?
he said,
Are you seeing kinematics in the question?
yes, the distance.
Of two things. So you can that should tell you that the difficulty level is increasing.
Mm.
So they are combining two different concepts. One concept from laws of motion and the other concept from kinematics. Okay, so a wooden block of mass 5 kg is at rest on a smooth horizontal table 1.6 meters from the edge of the table. So let's say from this side way to this side is 1.6 meters. The block is pulled directly towards the edge by a string. Let's say there's a string. The string is crooked. There's a string uh, with a force of 1 Newton. There's a force of 1 Newton. Now, with this information, we should be able to calculate acceleration. It's okay.
Mm. Mm.
Okay, so 1 is going to be equal to the mass, which is 5, times acceleration, which is a. A now becomes 0.2 meters per second squared. If my math is correct, that's 0.2 meters per second squared.
Mm.
Okay, so from this, we're told to calculate the time taken. This is where it takes us to kinematics. So let's set up a SUVAT. So
Yeah.
setting up that, let's fill in the values. What's going to be S?
S is 1.6.
1.6. U,
U is 0.
uh, acceleration is
Zero
0.
point 0.2.
So without the knowledge of the laws of motion, you can't solve this question because we're taking this value and transferring it to the kinematics. So if you get this value wrong, it means that you're going to get a question wrong. And well, that is how your past questions actually are played. One question can contain about four different concepts. So a concept from kinematics, a concept from forces, a concept from force and laws of motion. Naturally, or let me say, in most cases, the laws of motion are really connected to the forces, resultant of resolution of forces. So with a less understanding of that, it's going to be a little bit difficult for you to go through this successfully. But I know you good and you can take it. You can take the pressure. Okay, so we can find t in this case by using s equal to ut plus half at squared, and s is 1.6, u is 0 plus 1 over 2 of 0.2, and multiply by time. That should get you something nice. So
Yeah.
1.6.
4.
Okay, so the time is equal to 4 seconds. And that answers that question as well. Any question with this, please?
No.
Okay, so let's see question number 5 out of 10 for the horizontal surface question. Okay, this is interesting. A small seaplane of mass 8,000 is traveling with horizontal speed u meters per second when it lands on the sea. The plane is brought to rest by a water resistance of 960 newtons and 600 meters. Calculate the value. Now, Derek, there was a particle moving, uh, and all of a sudden, so let's say if the particle is moving, and all of a sudden the particle is not moving again. It got to a time the particle wasn't moving again. Was the particle accelerating or decelerating?
Decelerating.
Accelerating. Okay, good. So that should tell you that we moving from F equal to MA to F equal to MD because we didn't get deceleration. But anyway, let's
Mm.
assume that we don't even know that we don't get deceleration. Um, sorry about that. Sorry about that. Sorry. Okay, let's assume that we don't even know that we're going to get deceleration, and let's see what this is telling us. So a small plane. How will I even draw a plane? Hey, I'm doing well. Okay, so this it has spotted. But anyway, it's a plane.
Mhm.
A seaplane. Do you know a seaplane?
Yeah. The ones that can land on the sea.
Yes, yes, yes. So a seaplane lands on the sea. At that very moment where it lands, that is where we're going to take that under consideration. So let's say that it lands at this point. This is the landing point of the plane. Now the force at which this particle possesses, the resistance of the water is 960 newtons. So if the particle is moving forward, the resistance is going to move backwards. Do you agree?
Yeah.
960 newtons. So with this one, if our forward movement is positive, then it means that the resistance is negative. Do you agree?
Yes.
Okay. So at this point, we've got only one force over there. So 960, there is no force in this direction. But this force is actually moving in the negative direction. So the net force over there, the net force over there is going to be negative. Do you agree? There is no
Yeah.
other force. Yeah, the net force is going to be negative. So let's say the force is 960 newtons as given in the question. Now we know that net force is equal to mass times acceleration. So F equals to, in this case, I don't even need to write the F. 960, negative 960 is going to be equal to the mass of the particle, which is 8,000 kilograms, times acceleration, and you solve for acceleration and you get negative, that should tell you that there is going to be a reduction in speed. So another way to solve this question is, because this is a deceleration question, you should even know, you should know that there is deceleration without anyone telling you that the question is the deceleration, because something was moving and it stopped. The only reason it stopped was the speed was reducing. If the speed wasn't reducing, there is no way it's going to stop. So that alone should tell you that there is going to be deceleration. So with this one, looking at this and not even analyzing the question as, okay, forward movement is positive, backward movement is negative, forces, the vector is something, you can say that, okay, one force was given, that is 960, but this particle is going to be, will experience deceleration, not acceleration. So instead, we're saying that the force is going to be equal to mass times deceleration. I'm using D for deceleration. So in this
Mm.
case, the mass is going to be 8,000 and D. And you find D, what do you get for the A in this case?
0.12, negative 0.12.
0.12. And thus you get a deceleration as 0.12. All of this, negative acceleration implies deceleration. So if
Mm.
you don't really want to worry yourself with the negatives, you can do it this way. I will advise you to go with the negative. It makes the work presentable. F equal to MD, D can be taken as distance, those kind of things. You need to
Mm.
do an explanation of your parameters and other things. But it's the same idea. So at the point where it lands, that is where you're going to take that under consideration. Another way to see this too is looking at the point where it stops. When it stops, the only way this is going to stop is when the forces cancel each other out. So this is going
Mm.
to be 960 as well. So the end point and the start point and the end point, the forces will be the same, which will cancel each other out. And all of this will come out getting you this. So with this one, you can say that at the point that it stops, the force of the particle is going to be 160. But the only problem with this one is that if you don't take care, you start analyzing the question as the net force to be zero. That's going to be the problem over here, because this force is going to be 960 and this force is going to be 960 when it stops. So with this one, you can say that the net force is going to be zero, which is not the case. Which is not the case. So it's best to analyze it at the starting point, not the end point. If you're analyzing it at the end point, the force you're going to use now is not going to be a net force. The question will be, what force is it going to? Are we? What force is required to make this object to stop? That is how you're going to analyze the question. So that is if
Mm.
you are using the ending aspect of the question instead of using the starting aspect. So the force required to make this object to stop will be the same as the force the object started with. So in this case, it's going to be 960 Newton. Then, because the particle is decelerating, you are not going to use F equal to MA, but instead F equal to MD. Then you solve the question and you're good to go. Is that okay, please?
Mm.
Is that okay?
Mhm.
Okay, so it's your choice to make. I've taught you three different ways to analyze this question. I always will advise you to analyze it using the very first way. This way is actually very very confusing. The last one I taught you is very confusing. If you don't really know what you are doing, it's likely you're going to mess it up. Okay, so that's for that question. We are not done. We were told to do some kinematics somewhere. Calculate the value of u. So having the acceleration and other styles, we should be able to set up our SUVAT.
So, but
So
how do you know that is a constant acceleration?
constant acceleration. Well, the question never said anything about that, and we are not doing work, energy, and power. So assuming it was work, energy, and power, we would have used something else, change in kinetic energy, those kind of things. That is what is going to make the work, energy, and power a little bit complicated, because they don't tell you that the acceleration is constant, and you end up using kinematics assuming that the acceleration is constant. Are you getting me?
So for these ones, we can assume acceleration is constant.
We've not done work, energy, and power. The other way to solve this question will be using work, energy, and power.
Ah, okay, okay.
And we've not done work, energy, and power. So assuming we've done work, energy, and power, and you solve this question using this, your assumption is going to be that the acceleration is constant, and you may lose marks for it. It's in the marking scheme. So if the student assumes that the acceleration is constant, mark if it's out of 5, mark 3 out of 5, or mark 4 out of 5. It's always there in the marking scheme. But at this point, it's not done work, energy, and power, so we don't know how to treat things when the acceleration is not constant. Is that okay?
Mm.
Okay, good. So let's go through with this one. The distance traveled by the particle is 600 meters. The u is still u. The velocity, that is the final velocity, is 0, and the
Zero.
acceleration is 0.1.
Negative.
You're looking for u. So I can say v squared is equal to u squared plus 2as. This my 2 looks funny. Plus 2as. So 0 is going to be equal to u squared minus 2 of 0.12 and times 600. And we should be able to solve this using the calculator. U should be equal to square root of 2 times 0.12 times 600. Okay, this I got 12. I got 12 meters per second as an answer. Any confirmation, please? Can you confirm the answer? Is it 12?
Yeah, so
Okay, good. Then let's move on to the next question. So far, you can see the difficulty level is actually increasing. Question number 6. A toy car of mass 0.35 kilograms is moving with a velocity of 2 meters per second and comes to rest after it traveled 3.5 meters in a straight line on a horizontal floor. Calculate the resistance force that
that's
slows down.
account.
Okay, even without, I don't really think they should have even added that statement. Slowing down the car. The car started from with a speed and it's now coming to rest. So definitely there's going to be a deceleration. So some of those things you need to pick it up from the question. Even if the question doesn't say that there's going to be deceleration, you should know that by just reading the question that, hey, this particle is not increasing in speed, it's actually reducing in speed. So you should be able to work your way around that. Okay, so let's see what we can do with this one. Definitely going to do kinematics because I can see, what's the name? Speed over
Velocity.
there. Velocity, yeah, thank you. A toy car of mass. So, okay, so this, the mass, the toy car, 0.35 kg with a velocity of 2 meters per second. Started from rest and traveled a distance of 3.5. So from this side way to maybe this side is 3.5 meters. 3.5 meters. Now this is moving on a smooth surface, right?
Yeah, so
Was it said? As in, comes to rest. No, it's not.
horizontal.
It's not even moving on a smooth surface.
Maybe that's what stopped it. It also contributed in it stopping.
Yes, yes, yes. Okay, so a center of mass, blah blah blah, comes to rest after. Okay, so this question is going to be something else. The reason is that with this question, you need to do kinematics before you can solve it.
Mm.
The previous ones, let's say this is a resistance. We solved the question and we continued using kinematics, but then we want to start using kinematics. The reason is that I was given 3 items of kinematics. I don't know if you noticed
Yes.
3 items over there. So I got the final velocity, which is 0, the initial velocity, which is 2, the distance traveled, which is 3.5. So definitely I'm going to need acceleration. But this value, even before calculating for this, I know it's not going to be acceleration. It's going to be deceleration.
Mm.
Seeing that from this to the initial velocity is greater than the final velocity, there was a reduction in speed. So I should be expecting to get a value that is negative. So any positive value should tell me that what I'm doing is wrong. Okay, so with this one, we can use v squared again. V squared is equal to u squared plus 2as. And v squared is 0. U squared is 2 squared, which is 4. Let me just write a 4 over there. Plus 2. The acceleration is a, and the distance is 3.5. So, and that should give you an acceleration of negative 4 over 7. Yeah, I think my math is negative 4 over 7. Now with this one, we will be able to find the net force or the resistance force. So with the resistance, we know that the force equal to MA, and the force is, let's say, we don't know the force. Let me use R for the resistance. So R for the resistance, the mass of the particle is 0.35, the acceleration, which is negative 4.7, and the resistance is going to be equal to
Negative 0.2 newtons.
negative 0.2 newtons. But actually, the resistance is 0.2 newtons. The resistance is 0.2 newtons. This negative is just showing direction, so it's moving towards its opposite side. Are you getting me?
Yeah.
Okay, so negative resistance, negative 0.2. You should know
Can
the
you get
meaning of
negative force?
negative force. Just is showing the direction. That's what I was
Oh,
trying to tell you, that this negative over there is just telling you that it's moving in the opposite direction. So if there's our direction of motion, this is positive. It means that the resistance is moving towards this
yeah,
side.
yeah,
Is that okay?
yeah.
Good. So that answers that question too. Is your computer a Chromebook or a
It's a
laptop?
Chromebook.
It's a Chromebook. Oh, okay. I want to give you the what's the name? The application so that you don't really copy much. So that I get the
Um,
questions straight away. So how do you get the questions? You take screenshots.
yeah.
Oh, okay, okay. Okay, let's see this one. A porter at a railway station is dragging a suitcase of mass 82.5 kilograms along a platform with an acceleration of 0.175 meters per second squared. The horizontal force he that he exerts is 170 newtons. Find the frictional force between the floor and the tram. That's going to be interesting. Okay, so there's uh, okay, this has got a mass of 82.5. There's going to be a frictional force, we're told. So there's a frictional force. And what else? We're given a force of this again, a force of 170 newtons. And the question also said something about acceleration, 0.175 meters per second squared. Okay. How do you think we can find the frictional force over there?
You do it like net force equals to mass times acceleration. So 170 minus F is equal to 82.5 times 0.175. And you
That
find
is,
F.
yes, that is very good. So the net force is 170, the direction of motion minus F, that's the friction, times the acceleration. Oh, so there's the net force, sorry, 170
Yeah.
minus F going to be equal to the mass times acceleration, 82.5 times 0.175. And that should, you should be able to manipulate your way through and get me an answer. So 82.5 times 0.175 plus, is it minus 170, sorry.
And 08.125.
Are you sure? I'm getting 155. Let me redo my calculation again.
Into 22.5 times 0.175.
0.175.
It's 175.
Yes.
Okay then.
Getting the force to be equal to
Minus 170. Okay, I'm getting 155.6.
let's say 6.
Oh,
Yeah,
yeah.
155.6 newtons. Okay, so there's one way of solving it. There's a straightforward way of solving it. What I will do will be first finding the net force and reason my way through. But that is very good. That is very good. It is very short, so I like this method. Oh, I would have found the net force first, the force acting in this direction. Then I ask myself certain questions. If the net force is this, then what is going to be the frictional force? And you'll be able to get your answer from there. But this is equally very good. So that answers this question. Can we move on?
Mm.
Okay, so question number 8. Okay. A particle of mass 2.5 kg is pulled in a straight line along a horizontal surface by a string parallel to the surface with an acceleration of 2.8 meters per second squared. Given that there is a frictional force of 4 newtons that opposes the motion of the particle, find the tension in the string when the particle is traveling at a speed of 3 meters per second. Oh, sorry. Find the tension in the string, full stop. Oh, I was reading along. When a particle is traveling at a speed of 3 meters per second, the string breaks. Calculate how far the particle will travel before coming to rest. Interesting question. There, try your hands on this one, and let's see how we're going to deal with this. So we've got about 3 minutes to solve this.
Okay, I got my tensional force in the string to be 11
11.
Newton.
How did you do it?
I did like the opposite of what we did for the previous one. Just that this time I did um F minus 4 is equal to 2.8 times 2.5.
Okay, and that got you an answer of 11.
11. Yes.
Okay, let me just, okay. Uh, yeah, the tensional force is 11. It's 11 newtons. So let's solve that of the tension. Let's solve that of the tension. So again, we've got a mass of 2.5. Let me just sketch. You don't really need to do the sketching, okay? The sketch, I like solving my questions that way. The sketch is just a representation to make your imagination easy. So that is what I normally do. It's pulled along a straight, blah, 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 with a string. I'm talking a lot. So the tensional force is T, and acceleration was given as 2.8 meters per second squared. Given that the frictional force is 4 newtons. So I can say that T minus 4 is going to be equal to the mass, which is 2.5, times the acceleration, which is 2.8. And you do that, and you get T to be equal to 11 newtons. Now the second part of the question is very interesting. The string now breaks. So any ideas? Anyway, there's the kind of questions you be getting in the connected particles. So two particles are connected, and all of a sudden the string breaks. So what is going to be the speed at which one particle falls down? You like it? It's interesting. Any ideas? Oh, you're stuck. Should we do it
Um
together?
yes, because I'm trying to see what happens when the string is torn. What happens to the force? I don't know.
Yeah, the force is now zero. There is no
It's
force
now
pulling.
0.
There is only
Um,
one force acting on the particle, which is the frictional force. Are you getting me? When the
mm,
string, so let me just draw another force. Okay, let me just clean this. What I've just done. There is the force diagram. So I've cleaned there is no tension again. There is no tension in the string. So this is the only force. Remember the airplane question?
yeah.
the way we found the deceleration.
Mm.
Okay, so this is similar to the airplane question. So there is no force again. So definitely the particle is going to come to rest because the speed eventually is going to slow down. There is no force pulling it. So with this one, I can say that F equal to md, or better still, negative 4. That is, the force is in this direction, so negative, is equal to the mass of the particle, which is 2.5, times acceleration. So basically, the acceleration is going to be negative 4 divided by 2.5, and that should give you negative 1.6. So the acceleration of the particle is negative 1.6 meters per second squared. Now with this, we can set up a SUVAT.
Mm.
So SUVAT, were we given a distance, any distance? No.
No, that's what you're supposed to find.
We are told that when the particle attains a speed of 3 meters per second, the string breaks. Is this a final or an initial distance? Sorry,
In,
velocity.
in, initial
Initial. That is very good. So initial 3, and the final was given as 0 because it came to
0.
rest.
Mm.
Yes, and we now found acceleration to be negative 1.6. So with these three values, we should be able to find s by using v squared is equal to u squared plus 2as.
Mm.
Find s. 0 is going to be equal to 9. That is 3 squared is 9 plus 2. The acceleration is negative 1.6, and the distance is s. So this should be 9 divided by 3.2.
You get 2.8125.
Okay, so s equal to 2.8125. Derek, are you getting the reasoning behind this question?
Yes, I can understand what. Yeah.
Come again. Okay, okay. Because we're really going to use this idea, and actually this is going to be in terms of free fall. The string is going to break in free fall, so it's going to be very, very interesting. Okay, so let's move on to the next question. We are almost through with the horizontal surfaces. So that's the last question of the horizontal surfaces. And with this one, so I'll give you um, a maximum of 4 minutes to attempt this question. No, 4 minutes is too less. Let's say 5 minutes. Is that okay with you?
Okay. Okay. A is 375.
A 375.
Mm.
Um, I didn't get that. I didn't get A to be 375. Okay, so let's solve this one. It's a little bit tricky. Once A didn't go well, it means that everything is going to be some way. So a goods lift of mass 750 kg can contain up to a maximum load of 1,200 kilograms. If lifted, sorry, the lift is raised and lowered by a cable, definitely a string. Using G equal to 10 meters per second squared, calculate the tension. So let's say that this is the good something. Let's say there's a good something. So we've got, and there's my rope. The mass of this particle. The first question, we're told that the find the tension in the cable when it's being raised with a full load. So this one is really, really, really full. It's at its maximum. So at its maximum, what is going to be the mass over there? The maximum.
1200.
So first 1,200, and the lift itself has got its own weight. And what's the weight of the lift? It was given to us in the question. This diagram, the blue one, has got a mass of 750, and it can contain 1,200 mass. So the combined mass in this
Now,
case,
wait, I don't understand. Isn't that the goods that the lift is carrying?
The lift can carry a goods with what's the name, with a mass of 1,200. So it can't take more than 1,200 mass kilograms of mass. So that is the goods that is being placed over there. But the lift itself, let's say this is the lift itself. The lift itself weighs, or let me say, the mass of the lift itself is 750. This is 750. Just this diagram, this is 750. So when it's empty, when there is nothing in it, this is the mass. The mass is 750.
Mm,
We are told that this has been filled to its maximum. And we know that the maximum that it can take is going to be 1,200, right?
yeah.
So I can now say the total mass in this case is going to be 1950. Is that okay?
Yeah.
Okay, so we can use this value to work out whatever we need to work out. So with this one again, the particle is moving upwards. Do you remember I was like the direction of motion comes first minus all the forces opposing the direction of motion. So in
Mm.
this case, the direction of motion is along the tensional force. Now, aside the tension force, which other force can you talk about?
The gravitational force.
The weight force here.
Mm.
So wait, so there's going to be 19500 because we were told that the gravity is 10 meters per second squared. Is that okay?
Yes.
So there is a combined weight. And since the particle is moving upwards, we can now say that T minus all the downward forces, 1950, after all that is the net force, is going to be equal to the combined mass, 1950 times the acceleration. The particle has got an acceleration of 0.5 meters per second squared. So this should get us the T. So we've got 1950 times 0.5 plus 19500, and I'm getting this one as 20,475. 20,475. Please confirm that for me. Newtons, of course. Is that okay? Hello, Derek.
Mm. Yeah. Yes.
Okay, so let's look at the second question. The second question is when this time the object is being lowered. So let me try to sketch under. Let me just divide the page and let me try to sketch this one again. So again, I've got my lift. Let's say this is my lift. This time the lift is empty. The lift is empty. So I can say that the mass of the lift is just 750. That's what we were told. Now with this one, that can get me the weight force, which is going to be 7,500, and the tensional force, T. And with this, we were told that this was lowered, so it's going down actually with an acceleration of 0.7 meters per second squared. So with this one, the acceleration is 0.7 meters per second squared. So with these values, we should be able to find the tension force. First, the net force, which is going to be 750. I think a different color will do. 7,500. That is the weight force minus the tensional force because the particle is moving downwards. This is going to be equal to the mass of the particle, which is 750 kilograms, times the acceleration in which the particle has got. So with this one, we solve for T. T is going to be equal to 7,500 minus 750 times 0.7, and that should give you T to be equal to 6975. Is that okay, Derek?
Yeah.
Okay, so that answers the second question. Let's see what we can do about The third one, the mass, find the mass if the tension is 15,200 newtons when the particle is loaded. Sorry, did I read that as particle? I mean, when the, I think that statement doesn't, let me read from the start. The mass of the load, if there is a tension of 15,200 meters when the partially loaded lift is being raised at a constant speed. At a constant speed. This is the first time this is coming up. Constant speed. That is going to be the first law of motion. Do you remember?
Mm.
Okay, so with this one, let me try to do it here and get a small space over there then do that. Okay, so let's try to sketch the diagram. With this, we're given the tensional force. Again, this is my lift. The mass of the lift is 750. The mass itself is 750. And this time we're told that this was partially filled. So we don't know the mass that was in there. So let's say that the mass is M. Do you agree?
Yeah.
Okay. Now the tensional force given to us is 15,200 newtons. What, we don't know the weight force. So the weight force, I can say that is going to be 750 plus M. That is the two combined weight, combined mass, sorry, times 10. This becomes the weight now. The combined mass times 10 will give us the weight. Now we're told that this is moving with constant speed. With constant speed, what can you tell me?
Acceleration is zero.
The acceleration is zero. So if acceleration is zero, it implies that the net force is also zero. After all,
Mm.
force is equal to mass times acceleration, right? So if
Yeah.
acceleration is zero, acceleration is going to multiply the mass, which is going to give us the net force to be zero. When
Yeah.
is net force zero? When is net
Um, when the object is at rest.
when it's at
Oh.
rest? Let's talk about numbers. It's correct. When net force is when object is at rest, the net force is zero. But any other thing, I think
If
when the
the
forces
if
are
they are
equal,
equal.
yes, if the forces are equal. So I can say that the only way this can attain a constant, what's the name, constant speed will be when the weight force is also equal to 15,200 newtons. So I can say that this now gives me 15200 to be equal to 750 plus m, that is the combined mass, times the acceleration, which is 10. So we can work our way through this one. This becomes 1520 is equal to 750 plus m. We subtract 750 from that, and I think it will equal to 770. Yeah, I think so.
Mm.
1520 minus 750. Yeah, it's 770, and that answers the question.
Mm.
Is that okay?
Yeah.
So this is a flat surface. This is a flat surface. So if this is strong, if the idea on this is strong, we can move on to the inclined plane. Is that okay, Derek?
Yes, please.
Okay, good. So that is the last question of the horizontal surfaces. You're almost through. You're almost through. Yeah, you're almost through. We solved 9 questions so far. Now, this aspect is not going to be super difficult. But before we tackle this one, let's see what we can do if you still recollect the inclined plane, because you're going to use it a lot from now. Majority of your questions too are based on inclined plane. Okay, so let's go to the inclined plane. Do you remember the forces acting on an inclined plane?
Yeah.
Okay, so if, let me guess. Okay, so So if this is inclined at an angle theta, give me the possible forces that you can get on this.
Um, direct like right underneath this is mg cos theta.
Okay, so it's called a force that is perpendicular to the plane. So perpendicular to the plane is mg cos theta, and parallel to the plane,
Mg sin theta.
good, mg sin theta. Any reaction,
Then there's normal reaction
normal reaction. It's actually the same line as this. Okay,
as
it's like
the mg. Yes.
R. And I also remember telling you that it's not always that R is going to be equal to mg cos theta.
Yeah.
Yeah. So if the force is acting at an angle, this is not always the case. Now again, we can get
That's very
another,
cool.
which is the weight force mg. You don't really use this one, the weight force. And if possible, there can be a pull or push, so a force F newtons, and friction depending on the direction of motion. So if the particle is going upwards, there's going to be a frictional force going downwards. So friction F max. And you shouldn't forget your friction. Friction is equal to mu R, the coefficient of friction times the normal reaction. Do you remember all this?
Yes.
Okay, so if the particle is going downwards, the friction is also going to be F max. So these are possible things on the inclined plane. With this idea, you should be able to solve all the questions. So you can now treat inclined plane as a flat surface. The only thing you should know that is on the inclined plane, mg sine theta should show. It's very important. Is one of the hidden forces that causes a lot of students to get questions under this wrong. So you have to be very vigilant when it comes to that. Okay, so let's just get over with that one. Let's see what we can do with the rest. So multiple forces. Okay, let's polish up our forces. So this is a very simple question. I know you can even answer. You are not supposed to use a pen. This object is at rest. What is going to be the value of Q?
Is a rest. Oh,
Yes.
for p it will
Yes.
also be
So
okay.
P is
P will be 30 and q
30
will be
newtons.
60.
Q will be 60 newtons. Other side, P will be
Other side, let me see. It will be 24.
good. P will be 24 because there are two upward forces and one downward force. The summation of upward forces is 24. And since this is at rest, the upward forces cancels the downward forces. So it's going to be the same. That is good. And Q. But it took a lot of time to figure that one out.
Yeah, I didn't see the arrows. Well,
Oh, okay. Okay.
yeah.
What's of Q?
Q will be a negative 18. Oh,
Or is that
18. Yeah. Yeah.
it's just 18. Okay, so that is just that for that question. So we're done with 1 out of 7. The next one, a box is pulled on a smooth. I think we've done this already. A box is pulled on a smooth slope with an acceleration a by a light inextensible string. Draw a diagram showing all the forces. That's what we just did.
Yeah.
Yeah, so we've done that one. Yeah, I like the way we are moving fast. The next one, a block of mass 5 kg rests on a rough horizontal plane. It's attached to a string that is inclined at an angle 30 degrees to the horizontal. The tension in the string is 27 newtons. Find the frictional force, acting on the block. Find the frictional force acting on the block. You should be able to do this one. You solve a lot of questions. But mind you, this is not inclined plane. You know, right? This is not inclined plane. You start the
Yeah.
question. Yeah, this flat surface is still flat surface.
Mm.
So it's just that the object, the force is now at an angle,
Mm.
but still flat surface. So let's say this. is at an angle, and an angle of 30 degrees. Okay, just 30 degrees. And the force over there is 27 newtons. And there was a frictional force, I say F newtons. Eric, I'm going to make this question interesting. Afterwards, find the coefficient of friction.
Mm.
Any ideas as to how to solve this question?
First I resolved horizontally so
Okay,
that I can find my tension, the actual force moving
okay,
in the right side. So that was 27 cos 30.
okay,
And that give me 27 root 3 over 2.
okay.
Then they said the block is at rest. So
Mhm. So I was just wondering where you're going to go again. So with this one, I can say that the frictional force, this is what I was actually expecting to say. The frictional force is going to be equal to
yeah,
27 cos 30. That's all. 27 cos 30 and you're good to go. And that should give you something like 23.4. This is actually testing you, it's refreshing your memory when it comes to the forces because you're going to need that a lot. Are you getting me?
yes.
It's just something called RPK, relevant previous knowledge. So 23.4 newtons. Now, if I tell you to find the coefficient of friction, you should know that friction is going to be equal to mu r. In this
Yeah.
case, r, what is going to
Will
be
be
r? That is
50.
going to be the
50.
percentage. So
How will be
this
50?
50, well, let's
Okay,
see.
50 plus
Yeah.
27 sine 30.
See, that's where you're going to get it. You're going to get it wrong. So this one is it a downward force or upward force?
We are
The
going to find
vertical.
output.
Yeah, this is going to be upward. So this is actually going upward. So you can see that R, that is the normal reaction force, R plus the force going upwards, which is going to be 27. Which one is it? Cos sine 30. Sorry, 27 sine 30. 27 times 30 is going to be equal to the weight force, which is going to be 50. So with this one, you can find R, which is going to be 50 minus 27 sine 30. Is that okay, Derek?
Yeah.
Yeah, because we now know the frictional force, I can say that 23.4 is going to be equal to mu R, mu times 50 minus 27 sine 30. This is just by the way. So I just, as a recap, then mu is going to be equal to 23.4 over 50 minus 27 sine 30. And you just input this on the calculator and you get an answer and you'll be good to go. Is that okay?
Yeah.
Good. Let's move on. We are almost through, I think, 4 questions more. Yeah, there's a real question. Let's have fun. So take your time and do just this question for me.
Mm.
A small block of mass 3 kg is being pulled up the line of greater slope of a rough plane by a string that is parallel to the slope. The slope is inclined at 30 degrees to the horizontal. A frictional force of magnitude 2.5 newtons opposes the motion of the block. The tension in the string, sorry, if the block accelerates at 0.5 meters per second squared, calculate in terms of G the tension in the string. We've got about 15 minutes to end the class, so let's be fast about this. Did you replace the missing force? There is one missing force.
You know the mg cos theta.
Sine theta. The force parallel to the plane. This force,
Yeah.
mg sine theta. It's always going to be missing. So if you are not careful, you're going to mess it up. The only way, if you are not careful, you are not going to mess it up will be when you are dealing with work energy and power. Actually, that mg sine theta won't really come into play over there because gain in gain in potential energy will take care of that one. Okay, so let's resolve these forces. Do you remember I was like it's going to be the direction of motion minus all the forces opposing the direction of motion.
Yeah.
So this force is actually going up the plane. So there's going to be T minus all the forces that opposes the direction of motion. So the first one is 2.5 minus the next force is going to be mg sine theta. The m given is 3. We are told to leave our answer in G. So G and sine theta. In this case, theta is 30. This is going to be equal to the mass times acceleration. The mass in this case is 3, and the acceleration is, what are you given acceleration? Yeah, we're given acceleration to be 0.5 meters per second squared. So times 0.5. So you should be able to manipulate this one. This is 1.5. 1.5 plus 2.5. It should be equal to 4. So tension is going to be equal to 4 plus 330 G. And sine 30 is 1 over 2. So there's going to be 3 over 2. So 3 over 2 is 1.5. 4 plus 1.5 G. And that answers the question. It's okay.
Yes.
Okay, good. Any questions so far? Is the concept okay?
Yeah.
Okay. Now let's see again. The forces are actually coming into play now. Have you seen this question? Check out the question. Yeah, it's an interesting question. A boat is being pulled along a canal by 2 horizontal cables attached to 2 horses. The mass of the boat is 800 kg. 1 horse pulls with a force of 35 newtons, and the cable is at an angle of 10 degrees to the banks of the canal. The other horse pulls with a force of 40 newtons. Ignoring any resistance to motion, find the angle that the second horse should pull at in order that the boat moves forward and does not get dragged sideways. That's interesting. Ignoring any frictional resistance, find the acceleration of the boat. I like the way you're looking on your screen. Any ideas as to how to do this one?
Well, I didn't get the question.
Okay, so there is this boat. And 2 horses are pulling the boat. They are pulling this in a way that this won't move sideways. It's going to move horizontally straight this way without moving up or down. That is the first thing. So that should tell you that this particle is not going to go upward or downward. So with the y component of the resultant, what do you think that would be?
Y component will be 0.
It will be 0. It's going to be 0. So first, let's start with the force diagram. There's a force diagram. So blah 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 blah. There's a force diagram. We are told that this boat is not going to move sideways, so the y component of the resultant is 0. This was given as 10 degrees. And this was given as theta degrees. We don't know this. So with this information, I should be able to find the y component of the resultant. And that is going to be zero because it's not going to go upward or downwards. So with this one, 35 newtons and there's 40 newtons. Let me start my solving process. So I can say that 35 upward forces minus downward forces will be equal to 0. That is, there is no resultant force in that direction. So 35 sine 10 degrees should be equal to 40 sine theta degrees.
So why
So
are you using sine?
we're resolving vertically. I'm
But I
resolving
thought
vertically.
you said it's not supposed to move
Yes,
sideways.
it's not moving. It's not moving sideways, so the resultant is 0. So
So
it
is it not
means,
supposed to be?
mhm.
Is it not the horizontal, like resolving horizontally that we are looking for?
Oh yes, but we are told to find theta. Without
Yes,
doing that, you
but
can't get theta. Mhm.
are we not supposed to use cos?
But I'm resolving vertically. Derek, see this diagram. This boat is not going to move this side or this side. The only way this will be in a straight motion is when the forces balances each other. That is, the top force balances off the downward force.
Mm.
So that's the only way this is going to move straight. So that is the first condition I'm using to solve the question. So for this one, I'm resolving towards, definitely you're going to resolve in y direction and x direction. In this case, the question is telling us that resolving in the y direction is 0. There is no resultant in the y direction because the boat is not going to move sideways it's not going to be dragged sideways from this side. So
Yes.
first,
So isn't don't you use cos when you are resolving in the x direction?
I'll come back to resolving the x direction. After all, that is what is going to give me the resultant force in this direction. But because of this theta, okay, let's resolve this in the x direction. Resolving this in the x direction is going to be equal to forces to the right minus forces to the left. So resolving in the x direction is going to be forces in the right to the right. Sorry. So this is going to be x5 cos 10 plus 40 cos theta. Are you getting it?
Yes.
With this one, you can see that we can't find theta over there. There is no way we can find theta. There is not a number.
Oh,
With this one,
that's why
because
you
of,
are using that. Okay.
yes, that's why we're given the condition that it's not moving sideways. So with this one, I can now find my theta, then substitute that value into this and get the resultant in the x direction.
Mm.
Okay. So with this one, dividing both sides by 40, I can say that sine theta is going to be equal to 35 sine 10 degrees over 40. And sine, you should be able to find theta over there. So theta is going to be equal to the sine inverse of that. Use the calculator for that quickly. So 35 sine 10 divided by 40, sine inverse of that. And I'm getting 8.7, is it 74? 8.74. 8.74. That is that's 8.74. Is that okay?
Mm. Mm. Checking.
So with that value, yeah, please confirm for me so that we
Yes.
continue. Is it correct?
That's yes.
Okay, so with that value, I can now find the resultant in the x by substituting the value over there. If possible, substitute up to 4 to 5 decimal places, okay? So that we get a more accurate answer. So 35 cos 10 plus 40 cos 8.74. So 35 cos 10 plus
I'm getting
40 cos
74.
74. Exactly.
It's 74.0038.
0038. Okay, let's use this one. There's a more accurate answer. Okay. So now this is the direction of the net force, that is 77034. We can now use this value to find our, what's the name, the acceleration. So I can now see that 74.0038 is going to be equal to the mass of the object, which is 800, times the acceleration. Now dividing both sides by 800, we should get the acceleration to be
0.093.
0.9225. That's what I got over here. I use the entire figure. Okay. Are you getting this?
Yes.
Okay, that is good. You are almost true. Almost true. Um, yeah, my time is almost up with you too. Okay. Okay, we left with two more questions. Two more questions. Maybe I'll leave the question 7 for you to. It's a little bit complicated, and we don't really have much time. Then maybe when we meet on Saturday, we talk about that. So it means that on Saturday we're going to do connected particles. Connected particles, we solve the past questions. And connected particles is actually we done. The only thing I'm going to tell you about connected particles, I've told you already. Look at the direction of motion. The direction of motion is going to determine how your equation is going to be like. So if it's moving upward, it's going to be the upward forces minus the downward forces. That is going to be equated to the mass and acceleration, the product of mass and acceleration. And the rest is kinematics. That's one of the reasons why I spent much time on the kinematics with the past questions so that you get used to difficult and complicated questions. Anyway, there are more questions for you to solve, and I know you can do that for me. Okay, let's see that the body of mass 5 kg is released from rest so that it slides down the line of greater slope of a smooth plane inclined at an angle of 25 degrees to the horizontal. It is connected to a light inextensible rope. Light inextensible, a rope. Okay, a rope that inclined to the plane at angle of 10 degrees. That is interesting. The tension in the rope is 8 newtons, taking G as 10 meters per second squared. Calculate how far it will travel in 6 seconds. So first, let's see if you can get an acceleration over there. Now, this question is not so difficult. Let's see if you can get an acceleration. Okay, so this is the direction of motion. Definitely there is a force that is it's not showing, mg sine theta. So please be very careful. That is going to be 50 sine 25. Are you getting me there? Okay, so because this is the direction of motion, it's going to be the forces in this direction minus all forces in the opposite direction. So 50 sine 25 minus all forces in this direction. But with this direction, there is only one force, and this force is inclined to an angle. So we need to resolve that force. And resolving that force is going to be 8 cos 10 degrees. This is now going to be equal to the mass of the object, which is given as 5 times the acceleration, which you don't know. So with this one, we should be able to find A. And that answers the question. It's not so difficult. Sine 25 minus 8, 10. The answer divided by 5. And I'm getting the acceleration to be 2.65. 2.65. So 2.65 meters per second squared. Is that okay? Good. So with this one, we're told to find how far, so distance. Kinematics comes in again, so Suvat. So this question is actually taking 3 concepts under consideration. The first concept was the forces. The second concept is the laws of motion, and the third concept is kinematics. So you see, just this question, it contains three things that you should know, and this is just a textbook question. So just imagine a past question. You can take about four concepts for you to answer that question. Okay, so let's fill in the blanks. The time was given as 6. The acceleration we got is to be 2.65. And what else? What else? What else? Slides from rest, so u is 0. Using s equals ut plus affinity squared, you should be able to get the s. S is going to be equal to 0 plus 1 over 2. The acceleration is 2.65 and the time is 6 squared. So s should be
47.7.
7.7 meters, and that answers that question. So my time with you is up actually, and it's okay. This question is a little bit complicated. You can check the book I gave you. It's chapter 5 and it's 5.3. Exercise 5.3, the last question. It's a little. It's not that complicated though, but that's the only question I'm leaving you with today. Then when we meet on Saturday, we solve this one. Then we solve questions on connected particles. On Tuesday and Thursday, we solve the past questions. And on Saturday again, we do momentum. And we're done with 4 out of 5 topics.
Mm.
Okay, so that is all for today's class. Keep it up yourself. You look tired. Yeah, go and take a bath and rest. You'll be fine. Okay. Bye-bye.
Bye.